I want you to do something for me right now. I want you to look at something near you. It could be your phone, your wall, a cup of coffee, your own hand. Just look at it. You see it, right? It is there. It is solid. It is real. Now close your eyes. Is it still there? You would say yes, obviously. Of course it is still there. That is common sense. That is what every human being who has ever lived would say. But here is where things get deeply, profoundly, almost violently strange. According to the most widely accepted interpretation of quantum mechanics, the most successful and accurate scientific theory ever created by human minds, the answer to that question is not obvious at all. In fact, according to the standard interpretation that has dominated physics for nearly a century, that object you are just looking at does not have definite properties when you are not observing it. It is not that we simply do not know its properties. It is that it does not have properties. It exists in a ghostly, undefined, smeared-out state of pure possibility, and it only snaps into a definite, concrete reality when someone or something observes it. The moon, the stars, the chair you are sitting on, the atoms in your body. According to mainstream quantum mechanics, none of these things have definite properties until they are measured, until they are looked at, until they are observed. And no, I am not making this up. I am not exaggerating. I am not taking things out of context. This is literally what the founders of quantum mechanics believed and taught, and it is what most physicists are still taught today. Now, I know what you are thinking. That sounds insane. That sounds like something out of a bad science fiction movie, not serious physics. And you are right to think that. Because it does sound insane. And here's the thing, some of the greatest physicists in history also thought it sounded insane. Albert Einstein thought it sounded insane. Erwin Schrödinger, the man whose equation is the foundation of quantum mechanics, thought it sounded insane, and in 1952, a physicist named David Bohm did something extraordinary. He published a paper that essentially solved this problem. He showed that you do not need to believe in this insanity. He showed that particles can have definite positions at all times. He showed that the moon is there when nobody looks. He showed that reality is real. His solution was elegant, mathematically rigorous, and it reproduced every single prediction of standard quantum mechanics perfectly. Every single one. Not approximately, exactly. And what happened to David Bohm and his solution? It was suppressed. It was ridiculed. It was buried. The man himself was exiled from the United States, his passport confiscated, his career nearly destroyed, and the most powerful physicists in the world essentially agreed to pretend his work did not exist. Not because it was wrong, not because it had errors, not because it failed any test, but because it threatened their authority, their philosophy, and their legacy. This is the story I am going to tell you today. And I need you to understand something before we begin. This is not a conspiracy theory. This is not speculation. This is documented, verified, published history. The letters exist. The quotes are on record. The papers are available for anyone to read. What happened to David Bohm and his solution to the measurement problem is one of the greatest scandals in the history of science. And the fact that most people have never heard of it is itself part of the scandal. So, today, we are going to go deep. We are going to go deeper than most physics courses will ever take you. We are going to start at the very beginning, with the birth of quantum mechanics itself, and we are going to trace the entire story, every twist, every betrayal, every moment of genius, and every moment of cowardice, all the way to the present day. We are going to understand what the measurement problem actually is, why it matters, why it is the deepest and most disturbing unsolved problem in all of physics. We are going to understand the Copenhagen Interpretation, the official answer that is not really an answer at all. And we are going to understand how it became dogma, how it was enforced, and how it silenced dissent for decades. We are going to understand David Bohm's solution, pilot wave theory, in deep, clear, vivid detail. We are going to understand exactly how it works, exactly why it solves the measurement problem, and exactly why it is just as valid as any other interpretation of quantum mechanics. And then we are going to understand the suppression, who did it, why they did it, how they got away with it, and what it cost the world. And finally, we are going to understand the stunning comeback, the vindication, and the mind-blowing implications of Bohm's ideas for our understanding of reality itself. This is going to be a long journey, and I would not have it any other way, because this story deserves to be told properly, completely, with every detail and every nuance. So, get comfortable. Grab whatever you like to drink. Settle in, because by the end of this video, you will never see reality the same way again. And I mean that literally. Before we dive in, I want to know something. Where are you watching this from right now? What city? What country? Drop it in the comments. I ask because every time I do this, I'm amazed. This community spans the entire planet, and there is something beautiful about people from every corner of the world coming together to think about the deepest questions in science. And if you are new here, welcome. This is what we do. We do not do surface level here. We go deep. We go where most channels will not go. We ask the questions that most people are afraid to ask. So, if that resonates with you, you know what to do. Subscribe, hit that bell icon, and let us begin this journey together. To understand the measurement problem, we first need to understand the world it was born into. We need to go back to the beginning, to the world before quantum mechanics, to the universe as physicists understood it at the end of the 19th century. And that universe was a magnificent, awe-inspiring, deeply comforting machine. It was the universe of Isaac Newton, the universe of classical physics, and it worked like a perfectly engineered clock. In Newton's universe, everything was predictable. If you knew the position and velocity of every particle in the universe at any given moment, you could, in principle, predict the entire future and reconstruct the entire past. Every planet in its orbit, every apple falling from its tree, every wave crashing on every shore. All of it was the inevitable consequence of the laws of motion and the initial conditions. There was no randomness, no uncertainty, no ambiguity. The universe was deterministic. It was a machine. And if you understood the machine, you understood everything. This idea was captured most vividly by the French mathematician Pierre-Simon Laplace, who imagined a hypothetical being, now known as Laplace's demon, that knew the position and momentum of every single particle in the universe. Such a being, Laplace argued, could calculate the entire future and the entire past with perfect accuracy. Nothing would be hidden from it. Nothing would be uncertain. The universe would be an open book, readable from beginning to end. And this was not just a thought experiment. This was the genuine belief of physicists for over 200 years. The universe was a clockwork, and physics was the study of the gears. And the clockwork worked. It worked spectacularly well. Newton's laws predicted the motions of the planets with breathtaking accuracy. They predicted the tides, the trajectories of cannonballs, the behavior of gases, the strength of bridges. When Neptune was discovered in 1846, it was found not by looking through a telescope first, but by calculating where it must be based on the gravitational perturbations of Uranus. The mathematics predicted the planet before anyone ever saw it. That is how powerful classical physics was. That is how reliable the clockwork universe seemed. But there was something lurking beneath the surface. something that the beautiful clockwork could not explain, and it had to do with something as simple and everyday as the glow of a hot piece of metal. When you heat a piece of iron, it starts to glow. First a dull red, then orange, then yellow, then white. This is called black body radiation, and it was one of the most basic phenomena that physicists at the end of the 19th century were trying to understand. Classical physics, using the principles of thermodynamics and electromagnetism, made a prediction about how energy should be distributed across different frequencies of this radiation, and the prediction was catastrophically, absurdly wrong. Classical physics predicted that as you went to higher and higher frequencies, shorter and shorter wavelengths, the energy should increase without limit, approaching infinity. This meant that a hot piece of iron should emit infinite energy in the ultraviolet and beyond. Obviously, this does not happen. Your toaster does not destroy the universe every time you make breakfast. This failure of classical physics was so dramatic, so complete, that it was given a dramatic name, the ultraviolet catastrophe. And it was the first crack in the foundation of the clockwork universe. In the year 1900, a German physicist named Max Planck found a way to fix this problem. But his fix required him to do something deeply strange, something that went against everything classical physics stood for. Planck proposed that energy is not continuous. It does not flow smoothly like water. Instead, it comes in tiny, discrete packets, which he called quanta. The energy of each quantum was proportional to the frequency of the radiation, connected by a new fundamental constant that would bear his name, Planck's constant, denoted by the letter h. This tiny number, approximately 6.626 times 10 to the negative 34 joule seconds, would turn out to be one of the most important numbers in the universe. By assuming that energy comes in these discrete quanta, Planck was able to derive a formula that perfectly matched the observed spectrum of black body radiation. The ultraviolet catastrophe was averted. But at what cost? Here is the fascinating thing about Planck. He did not believe his own idea. He did not think energy really comes in quanta. He thought it was a mathematical trick, a convenient accounting device that happened to give the right answer. He expected that someone would eventually find a way to derive the correct result without needing this strange assumption of quantized energy. He called his own discovery an act of desperation. He spent years trying to undo it, to find a classical explanation. He never found one, because the quantum was not a trick. It was a window into a deeper reality, and the universe on the other side of that window was nothing like the clockwork Planck had grown up with. 5 years later, in 1905, a young patent clerk in Bern, Switzerland, did something that would shake physics to its core. His name was Albert Einstein, and in that single miraculous year, he published 4 papers that would change everything. One of those papers was about the photoelectric effect, a phenomenon that had been puzzling physicists for years. When you shine light on a metal surface, electrons are ejected from the surface. This was known. But the details were strange. Classical physics predicted that the energy of the ejected electron should depend on the intensity of the light. Brighter light should mean more energetic electrons. But experiments showed something different. The energy of the electrons depended on the frequency of the light, not its intensity. Red light, no matter how bright, could not eject electrons from certain metals, but even dim violet light could. This made no sense if light was a continuous wave. Einstein's explanation was radical. He proposed that light is not just a wave. Light is also made of particles, tiny packets of energy that he called light quanta, later named photons. Each photon carries an energy equal to Planck's constant multiplied by the frequency of the light. When a photon hits an electron in the metal, it transfers its energy to the electron. If the photon has enough energy, high enough frequency, the electron is ejected. If not, no amount of photons will do the job. This beautifully explained the photoelectric effect. But it meant something shocking. Light, which had been conclusively proven to be a wave by Thomas Young's double-slit experiment over a century earlier, was also a particle. It was both. Somehow, impossibly, it was both. And here is an irony that I want you to appreciate. This paper, on the photoelectric effect, is what Einstein won the Nobel Prize for. Not for relativity, not for E equals mc squared, not for bending space-time, for showing that light is made of particles. Einstein helped create quantum mechanics. He was one of its founding fathers, and he would spend the rest of his life trying to destroy it. Not because the mathematics was wrong. The mathematics was spectacularly right, but because of what it implied about reality, because of what it said about the nature of the universe, because of the measurement problem. But we are getting ahead of ourselves. To understand the measurement problem, we need to understand the experiment that contains, in the words of Richard Feynman, the only mystery of quantum mechanics. We need to understand the double-slit experiment. And I need you to pay very close attention here, because everything that follows, the measurement problem, the Copenhagen Interpretation, Bohm's solution, the suppression, all of it, flows from what happens in this experiment. Imagine a wall with two narrow slits in it, side by side. Behind the wall is a screen that can detect where particles land, like a photographic plate. Now, imagine you are firing tiny particles, let us say electrons, at this wall, one at a time. Each electron passes through the wall and hits the screen somewhere, leaving a tiny dot. If you do this with one electron, you get one dot. Seems straightforward. Now, if you fired bullets at a wall with two slits, what would you expect to see on the screen behind it? You would expect two clusters of bullet holes, one behind each slit. Two bands. That is what common sense predicts. That is what classical physics predicts. And if you close one slit and fire electrons through the other, that is indeed what you see. A single band behind the open slit. So far, so normal. But here is where everything goes sideways. When you open both slits and fire electrons one at a time, waiting for each one to hit the screen before firing the next, something impossible happens. You do not get two bands, you get an interference pattern. Bright bands and dark bands alternating across the screen, exactly like the pattern you would see if you sent waves through the two slits. Waves that pass through both slits spread out on the other side, and where the crests of one wave meet the crests of another, they add up and create a bright band. Where a crest meets a trough, they cancel out and create a dark band. This is wave interference, and it is a well-understood phenomenon. But here is the thing. You are sending electrons through one at a time. Each electron is a single particle. It cannot split in two and go through both the slits. It cannot interfere with itself. And yet, after thousands of electrons have been fired one at a time, the pattern on the screen is unmistakably an interference pattern. The individual particles, each going through the slits one at a time, somehow collectively produce a pattern that only makes sense if each one went through both slits simultaneously and interfered with itself. Let me say that again, because it deserves to be said again. Each electron, one at a time, seems to go through both slits at the same time, interfere with itself, and then land as a single particle on the screen. It travels as a wave and arrives as a particle. This is not a metaphor. This is not a simplification. This is what actually happens in the laboratory, and it has been confirmed in countless experiments with electrons, photons, neutrons, and even large molecules. The double-slit experiment is one of the most replicated experiments in the history of physics. But wait, it gets stranger, much stranger. because scientists, being scientists, naturally wanted to know, which slit does the electron actually go through? So they placed a detector at the slits, a device that could observe which slit each electron passed through. And when they did this, the interference pattern disappeared. When they watched, the electrons behaved like particles, creating two bands behind the two slits, just like bullets would. When they did not watch, the electrons behaved like waves, creating an interference pattern. The act of observation changed the result. Let me be very clear about what this means. By simply looking, by simply gathering information about which path the electron takes, you change what the electron does. The electron seems to know whether it is being watched. When no one is looking, it does the wave thing, passing through both slits and creating an interference pattern. When someone is looking, it does the particle thing, passing through one slit and creating a simple pattern. The observer, the act of measurement, changes the outcome of the experiment. This is not supposed to happen. In classical physics, observation is passive. You can look at a planet without changing its orbit. You can measure a baseball's speed without altering its trajectory. Observation is something you do after the physics happens. It does not affect the physics itself. But in quantum mechanics, observation is active. It changes things. It seems to determine things. And this leads to a question so deep, so fundamental, so disturbing, that it has haunted physics for 100 years. What exactly is observation? What counts as a measurement? What does it mean to look? And if the act of looking determines reality, then what is reality when no one is looking? This is the measurement problem, and it is the deepest problem in physics. To understand the measurement problem precisely, we need to understand one more piece of the quantum puzzle, the wave function. In quantum mechanics, every particle is described by a mathematical object called the wave function, usually represented by the Greek letter psi. The wave function is not a physical wave like a water wave. It is a mathematical function that encodes all the information about the particle. Specifically, the square of the wave function at any point gives you the probability of finding the particle at that point if you were to measure it. Where the wave function is large, the particle is likely to be found. Where it is small, the particle is unlikely to be found. Where it is zero, the particle will never be found. Now, here's the crucial thing. The wave function evolves over time according to an equation discovered by Erwin Schrödinger in 1926, the Schrödinger equation. And the Schrödinger equation is perfectly deterministic. Given the wave function at one moment, the Schrödinger equation tells you exactly what the wave function will be at any future moment. There is no randomness in the Schrödinger equation, no probability, no uncertainty. It is as deterministic as Newton's laws. The wave function flows forward in time like a river, smooth and predictable. And this wave function can describe a particle being in a superposition, that is, in multiple states at the same time. An electron can be in a superposition of being at position A and position B simultaneously. A photon can be in a superposition of going through the left slit and the right slit. This is not a metaphor. The mathematics describes this literally, and experiments confirm it. But then something happens that the Schrödinger equation cannot explain. You make a measurement, you look at the electron to see where it is, and suddenly the wave function collapses. The smooth spread-out wave function, which described the electron as being in many places at once, suddenly snaps into a single, definite state. The electron is found at one specific location. The superposition is gone. The probabilities have resolved into a single reality. And this collapse is completely different from the smooth evolution of the Schrödinger equation. It is sudden, instantaneous, discontinuous, and random. You cannot predict where the electron will be found. You can only predict the probabilities. And there is nothing in the Schrödinger equation that produces this collapse. The equation describes smooth evolution. Collapse is something else entirely, something that is just added on top, without explanation, without mechanism, without justification. And this is the measurement problem, stated precisely. There are two fundamentally different processes in quantum mechanics. Process 1 is the smooth, deterministic evolution of the wave function according to the Schrödinger equation. Process 2 is the sudden random collapse of the wave function when a measurement is made. Quantum mechanics uses both processes but provides no explanation for when one process takes over from the other, no explanation for what constitutes a measurement, and no explanation for why measurements cause collapse in the first place. The theory is schizophrenic. It has two incompatible rules, and no instructions for when to apply which one. Let me break this down even further because the measurement problem actually contains three distinct sub-problems, each one devastating on its own. The first is the problem of outcomes. The wave function describes a superposition. The electron is in many places at once. But when we measure, we always get a single, the definite outcome. Why? What causes the many to become one? The Schrödinger equation never produces this. If you apply the Schrödinger equation to the entire measurement process, the electron, the detector, the physicist, everything, you just get a bigger and bigger superposition. The measurement apparatus ends up in a superposition of detecting the electron at position A and detecting it at position B. The physicist ends up in a superposition of seeing result A and seeing result B. The mathematics never gives you a single definite outcome, but we always experience one. Why? The second subproblem is the problem of probability. When the wave function collapses, the probability of each outcome is given by the Born rule. The probability equals the square of the amplitude of the wave function for that outcome. This rule works perfectly. It has been tested in millions of experiments and never failed. But where does it come from? There is nothing in the Schrödinger equation that generates probabilities. The equation is deterministic. Probability appears only when collapse happens. But if we do not understand collapse, we do not understand where the probabilities come from. The Born rule is an additional postulate, bolted on from outside, with no derivation from the underlying dynamics. The third subproblem is the problem of the boundary, sometimes called the problem of the cut. Where is the line between the quantum world and the classical world? Where does quantum superposition end and definite reality begin? Is it at the level of atoms, molecules, cells, brains, the universe? In 1932, the mathematician John von Neumann proved something remarkable. The boundary can be placed anywhere in the measurement chain without changing the predictions. You can say the collapse happens at the detector, or at the physicist's retina, or at the physicist's brain, or nowhere at all. The mathematics does not care. It gives the same predictions regardless. But this means the theory provides no guidance about where the boundary is. It is arbitrary. And a fundamental theory of physics should not contain an arbitrary boundary between two incompatible kinds of evolution. This is the measurement problem. It is not a minor technical issue. It is not a philosophical quibble. It is a gaping hole in the foundations of the most important theory in physics, and it has been there since the 1920s. It is still there today. The official mainstream interpretation of quantum mechanics does not solve it. It does not even try. It just tells you not to worry about it. And that, as we are about to see, is a scandal in itself. Now, I want to take you to a thought experiment that makes the measurement problem visceral, that takes it out of the abstract realm of mathematics and puts it right in your gut. This thought experiment was proposed in 1935 by Erwin Schrödinger himself, and it has become one of the most famous images in all of science. I am talking, of course, about Schrödinger's cat. Here's how it works. Imagine a sealed box. Inside the box is a cat, a radioactive atom, a Geiger counter, a vial of poison, and a mechanism that connects them. If the radioactive atom decays, the Geiger counter detects it and triggers the mechanism, which breaks the vial and releases the poison, killing the cat. If the atom does not decay, the cat lives. Radioactive decay is a quantum process governed by quantum mechanics. Before anyone opens the box to check, the atom is in a superposition of having decayed and not having decayed. And since the cat's fate is linked to the atom, the cat should also be in a superposition, simultaneously alive and dead. Now, most people first encounter Schrödinger's cat and think it was proposed to illustrate the weirdness of quantum mechanics. But that is wrong. That is a fundamental misunderstanding. Schrödinger proposed this thought experiment to show how absurd the standard interpretation of quantum mechanics was. He was not celebrating the idea that the cat is both alive and dead. He was saying, "Look how ridiculous this is." The cat is obviously either alive or dead, not both. And if quantum mechanics says otherwise, then quantum mechanics must be incomplete. There must be something it is not telling us. The thought experiment was meant as a criticism, not a celebration. And the target of that criticism was the Copenhagen Interpretation, the interpretation that dominates physics to this day. But the power of Schrödinger's cat goes beyond the absurdity. It exposes the measurement problem with surgical precision. When does the collapse happen? When the atom decays or does not decay? When the Geiger counter clicks or does not click? When the vial breaks or does not break? When the cat dies or does not die? When you open the box? When light from inside the box reaches your eyes? When nerve signals from your eyes reach your brain? When your brain processes the information? At what point does the superposition end and definite reality begin? The standard theory gives no answer. It cannot answer because it does not know what a measurement is. Every attempt to draw the line at some point leads to new problems, new questions, new absurdities. And it gets worse. Much worse. A thought experiment proposed by Eugene Wigner, one of the most brilliant physicists of the 20th century, took Schrödinger's cat and turned it into a full-blown existential crisis. Wigner imagined the following scenario. Instead of a cat, put your friend inside the box. Your friend performs the experiment, observes whether the atom has decayed, and sees a definite result. From your friend's perspective, there is no superposition. They see a definite outcome. But from your perspective, outside the box, your friend is in a superposition of having seen the atom decay and not having seen the atom decay. You are in a position analogous to Schrödinger outside the cat box. Until you open the box and ask your friend what they saw, your friend does not have a definite experience, according to the standard theory. But that is absurd. Your friend did have a definite experience. They did see something. Their consciousness did register a result. So who is right? Whose perspective determines reality? Is your friend's experience real before you observe it? And what if there is a third person outside, for whom both you and your friend are inside a box? You see where this goes. It is an infinite regress. Observers observing observers observing observers, all in superposition relative to each other, and no place where reality definitively begins. Von Neumann himself, the mathematical genius who formalized quantum mechanics, took this chain of reasoning to its ultimate conclusion. He showed that the mathematics allows you to place the collapse at any point in the chain, at the detector, at the observer's eyes, at the observer's brain, anywhere, without changing the predictions. the collapse point is, mathematically, completely arbitrary. And this led von Neumann and later Wigner to a startling suggestion. Perhaps the chain of superposition only breaks when it reaches consciousness. Perhaps it is the conscious mind that causes the wave function to collapse. Perhaps consciousness itself is the demarcation between the quantum and classical worlds. This idea, that consciousness causes collapse, is controversial, to put it mildly. Many physicists are deeply uncomfortable with it because it seems to inject subjectivity into physics, to make the human mind a fundamental ingredient of reality. But here is the thing. If you do not accept consciousness as the collapse trigger, you need to provide an alternative. And the Copenhagen interpretation does not provide one. It just says, collapse happens when a measurement occurs, and refuses to define what a measurement is. And so the measurement problem persists, a wound that is never healed, a crack in the foundation that has never been repaired. I want to take a moment here to emphasize something that often gets lost in popular discussions of quantum mechanics. The measurement problem is not just an abstract philosophical puzzle that theorists argue about in their ivory towers. It has real, concrete, practical consequences. Consider quantum computing, one of the most important technologies of the 21st century. A quantum computer works by manipulating qubits, quantum bits that exist in superpositions of 0 and 1. The power of quantum computing comes from maintaining these superpositions and using them to perform many calculations simultaneously. But here is the problem. Any interaction with the environment, any stray measurement, causes the superposition to collapse. This is called decoherence, and it is the single greatest obstacle to building practical quantum computers. If we truly understood the measurement problem, if we truly understood what constitutes a measurement and why it destroys superposition, we might be able to solve the decoherence problem and build quantum computers that actually work at scale. The measurement problem is not just philosophy. It is a multi-billion-dollar engineering problem. It is the reason quantum computers are still fragile, finicky, error-prone machines, instead of the revolutionary technology they are destined to become. Similarly, quantum cryptography, quantum teleportation, quantum sensing, all of these technologies depend on our understanding of measurement and collapse. The measurement problem touches everything in quantum physics. It is not a niche concern, it is the concern, the central concern, the foundational concern, and the fact that it has been swept under the rug for nearly a century is, in my view, one of the most extraordinary failures of the scientific enterprise. Now, I have laid out the problem, and I hope you feel the weight of it. This is not a small problem. This is the deepest, most fundamental problem in the most important theory in physics. The greatest minds of the 20th century, Einstein, Schrödinger, Feynman, Bell, Hawking, all acknowledged it. And for decades, the official response of the physics establishment was, essentially, do not worry about it. Do not ask about it. Just shut up and calculate. And the name for this official non-response, this shrug dressed up as an interpretation, is the Copenhagen Interpretation. The Copenhagen Interpretation is named after the city of Copenhagen, where the great Danish physicist Niels Bohr had his institute. And to understand the Copenhagen Interpretation, you need to understand Niels Bohr, because the interpretation is inseparable from the man. Bohr was, by all accounts, a remarkable figure. He won the Nobel Prize in 1922 for his model of the atom. He was a deep thinker, a passionate debater, and an incredibly persuasive speaker. His institute in Copenhagen became the epicenter of quantum mechanics in the 1920s and 1930s, attracting the brightest young physicists from around the world. Werner Heisenberg, Wolfgang Pauli, Paul Dirac, Max Born, they all passed through Copenhagen. And Bohr did not just teach them physics, he taught them a philosophy. a way of thinking about quantum mechanics that would become the dominant paradigm for a century. The core of the Copenhagen Interpretation can be summarized in a few key claims, though I should warn you that different physicists who call themselves Copenhagenists do not always agree on the details, which is itself revealing. The first claim is that the wave function does not represent physical reality. It represents our knowledge of reality, or our ability to make predictions about measurements. The wave function is a mathematical tool, not a description of what is really out there. The second claim is that particles do not have definite properties until they are measured. Before measurement, the particle exists in a superposition, and it is meaningless to ask which state it is really in. The question has no answer, not because we do not know the answer, but because there is no answer. The third claim is that quantum mechanics is complete. There is nothing deeper. There are no hidden variables, no underlying mechanism, no clockwork beneath the quantum randomness. The randomness is fundamental, irreducible, bedrock. The fourth claim, and this is where it gets really problematic, is that the act of measurement causes the wave function to collapse. But the theory does not define what constitutes a measurement. It does not explain the mechanism of collapse. It does not identify the boundary between the quantum and classical worlds. It simply asserts that collapse happens and moves on. And underpinning all of this was Bohr's philosophical principle of complementarity, which states that quantum objects have complementary properties, like wave and particle, that cannot be observed simultaneously. You can set up an experiment to see the wave nature, or you can set up an experiment to see the particle nature, but you cannot see both at once. And crucially, it is meaningless to ask what the quantum object is in itself, independent of measurement. There is no underlying reality to be described. There are only experimental arrangements and their outcomes. Now, I want to be fair to Bohr. He was grappling with something genuinely unprecedented. Quantum mechanics was unlike anything physics had ever encountered. The old classical intuitions clearly did not work. Particles are not like tiny billiard balls, and waves are not like water waves. Something fundamentally new was needed. And Bohr's insistence that we cannot simply project our everyday intuitions onto the quantum world was, in a sense, correct. But there is a difference between saying our old intuitions need to be revised and saying that we should stop looking for an understanding of reality altogether. There is a difference between intellectual humility and intellectual surrender, and the Copenhagen Interpretation, in my assessment, crosses that line. It does not solve the measurement problem. It declares the measurement problem unsolvable and then forbids you from trying. And here is where we come to the part of the story that most physics courses leave out, the part about power, politics, and the suppression of dissent. Because the Copenhagen Interpretation did not become dominant because it was the best interpretation. It became dominant because Niels Bohr made it dominant. Bohr was not just a physicist. He was an institution. He controlled the most important physics institute in the world. He had immense influence over funding, hiring, and publications. He was a mentor to a generation of physicists who went on to become professors and department heads at major universities around the world. And he used this influence, consciously or not, to promote his interpretation and marginalize alternatives. Young physicists who questioned Copenhagen were warned that they were wasting their time. Foundational questions about quantum mechanics were dismissed as philosophy, not physics. The culture of shut up and calculate was born in Copenhagen, and it spread through the global physics community like a virus. I do not want to paint Bohr as a villain. I do not think he was acting out of malice. I think he genuinely believed that his interpretation was correct, that probing deeper was futile, that quantum mechanics was complete. But the effect of his influence was to create an environment where dissent was not tolerated, where alternative ideas were not explored, and where an entire generation of physicists was trained to accept an incomplete answer as the final word. This is not how science is supposed to work. The most famous challenge to the Copenhagen Interpretation came from Albert Einstein himself, in a series of debates with Bohr that took place over many years, primarily at the Solvay conferences of 1927 and 1930. These debates are legendary, and they are often presented as a decisive victory for Bohr. But the truth is more complicated. Einstein's strategy was to propose thought experiments that expose the incompleteness of quantum mechanics, and Bohr's strategy was to find flaws in Einstein's thought experiments. And Bohr was very clever. He found flaws. He won the individual battles. But the war, the question of whether quantum mechanics is complete, was never settled by these debates. The most powerful shot Einstein ever fired was the EPR paper, published in 1935 with his colleagues Boris Podolsky and Nathan Rosen. EPR stands for Einstein-Podolsky-Rosen, and the paper's argument was deceptively simple but devastatingly effective. Consider two particles that have interacted and then separated. Quantum mechanics predicts that these particles are entangled. Their properties are correlated in a way that cannot be explained by any local mechanism. If you measure a property of one particle, you instantly know the corresponding property of the other particle, no matter how far apart they are. Now, Einstein argued, this presents a dilemma. Either measuring one particle instantaneously affects the other, which would violate relativity, since nothing can travel faster than light. Or both particles had definite properties all along, and quantum mechanics simply does not describe those properties. Einstein concluded the latter. Quantum mechanics is incomplete. There must be additional information, hidden variables that determine the particle's properties before any measurement is made. Bohr's response to the EPR paper was, to put it diplomatically, not his finest moment. His reply was long, convoluted, and many physicists then and now have struggled to understand exactly what he was arguing. He seemed to be saying that the concept of physical reality used by EPR was too narrow, that in quantum mechanics you cannot separate the properties of a particle from the measurement apparatus, and that therefore the EPR argument did not go through. But this response did not satisfy Einstein, and it should not satisfy us. Because Einstein's central point, that quantum mechanics might be incomplete, that there might be hidden variables beneath the quantum randomness, was never actually refuted. It was dismissed. It was waved away, but it was not refuted. And the irony, the deep and tragic irony, is that Einstein was right. Not about every detail, not about locality. As we will see later, Bell's theorem showed that any hidden variable theory must be non-local. But about the central claim that quantum mechanics is incomplete, that there is a deeper level of description, that particles can have definite properties at all times. About that, Einstein was right, and the proof came in 1952, from a man Einstein himself had encouraged, a man named David Bohm. But before we get to Bohm, I want to drive home just how problematic the Copenhagen interpretation really is, because many people who have been taught physics in schools and universities have absorbed it so deeply that they do not realize how problematic it is. They accept it as the established wisdom, the settled science, the way things are. And I want to unsettle that, because the Copenhagen interpretation is not settled science. It is a philosophical position with deep, unresolved problems. And the fact that it is taught as if it were established fact is, in my view, a failure of physics education. Consider the following. The Copenhagen interpretation says the wave function does not represent reality. It represents our knowledge. But whose knowledge? If two different observers have different information about a quantum system, do they have different wave functions? And if so, which one is right? The interpretation says particles do not have properties until measured. But what counts as a measurement? Is it when a photon hits a detector? When the detector registers a click? When a human looks at the detector? When the information reaches the human's consciousness? The interpretation provides no answer. It says quantum mechanics is complete. But complete descriptions of reality should not contain undefined terms, arbitrary boundaries, and unexplained processes. And the Copenhagen interpretation is full of all three. John Bell, the Irish physicist who would later deliver the decisive blow in this story, was characteristically blunt about the Copenhagen interpretation. He called it unprofessionally vague and ambiguous. He pointed out that the word measurement appears in the axioms of quantum mechanics but is never defined. He argued that a fundamental theory should not contain such undefined concepts. And he was right. Imagine if Newton's laws referred to pushes without ever defining force. Imagine if Maxwell's equations used the word disturbance without defining electric and magnetic fields. That is, in effect, what the Copenhagen interpretation does with the word measurement. It is a placeholder for an explanation that was never provided. A survey conducted at a Quantum Foundation's conference in 2011 asked physicists which interpretation of quantum mechanics they preferred. The results were revealing. Copenhagen received the most votes, but only 42%. Many worlds got 18%. Information-based interpretations got 24%, and 12% chose other or none of the above. This is not a consensus. This is not settled science. This is a field in disarray, a century after its founding, still unable to agree on what its most fundamental theory actually means. The idea that Copenhagen is the interpretation, that the matter is settled, that all serious physicists agree this is a myth that was created by the Copenhagen School and maintained by inertia, by textbook tradition, and by the culture of shut up and calculate. And it was into this culture, this environment of enforced orthodoxy and suppressed dissent, that David Bohm published his 2 papers in 1952, papers that would solve the measurement problem completely, papers that would show that reality is real, and that particles have definite positions at all times, that the moon is there when nobody looks, papers that would be buried for decades. Let me tell you about David Bohm. If you are enjoying this deep dive, if you are learning things that you never learned in school, things that your physics professors never told you, then I need you to do something for me right now. Hit that like button. I know it seems like a small thing, but it genuinely matters. It tells the algorithm that this content is worth sharing, and it helps more curious minds find their way here. And if you have not subscribed yet, this is the moment. Because we are about to enter the most extraordinary part of this story, and I promise you, what comes next will change how you see science, how you see physics, and how you see reality itself. David Joseph Bohm was born on December 20th, 1917, in Wilkes-Barre, Pennsylvania, a coal mining town in the northeastern part of the state. His father, Samuel Bohm, was a Hungarian Jewish immigrant who ran a furniture store. His mother, Frida, was Lithuanian. It was not a wealthy family, and it was not a particularly intellectual environment. But from a very young age, David Bohm was different. He was fascinated by the natural world, captivated by how things worked, consumed by questions about the nature of reality. He would later describe his childhood fascination with how streams of water merged and separated, how patterns formed and dissolved, how the world seemed to be in constant flux and yet maintained order. These early impressions would shape his thinking for the rest of his life. Bohm studied physics at Penn State and then moved to the University of California at Berkeley, where he became a graduate student of J. Robert Oppenheimer, the man who would later lead the Manhattan Project and become known as the father of the atomic bomb. Oppenheimer was a brilliant physicist and a charismatic teacher, and Bohm thrived under his mentorship. During World War II, Bohm worked at the radiation laboratory at Berkeley, contributing to the Manhattan Project through his work on plasma physics and the physics of deuterium. His work was so classified that he was not even allowed to write his own doctoral thesis. The results were locked away as military secrets. He eventually received his Ph.D. based on work that he himself could not access. After the war, Bohm joined the faculty at Princeton University, one of the most prestigious physics departments in the world. He was a rising star, recognized as a brilliant thinker and an exceptional teacher. And it was at Princeton that Bohm wrote a textbook that would change his life. In 1951, he published Quantum Theory, a comprehensive textbook on quantum mechanics. It was not just any textbook. It was, by many accounts, the clearest, most thoughtful, and most philosophically honest presentation of quantum mechanics that had ever been written. Even Einstein, who was famously critical of quantum mechanics, praised it. He called it the best clear exposition of quantum theory he had ever seen. The textbook faithfully presented the Copenhagen Interpretation, explaining it with a clarity and depth that no one had achieved before. But here is the irony that changed everything. By writing the best explanation of the Copenhagen Interpretation, Bohm came to understand its weaknesses more deeply than anyone. The act of explaining the theory with complete honesty forced him to confront its gaps, its undefined terms, its arbitrary boundaries, its hand-waving. He saw, with devastating clarity, that the Copenhagen Interpretation did not solve the measurement problem. It just dressed it up in philosophical language and declared it solved. And this realization troubled him deeply. After the textbook was published, Bohm sent a copy to Einstein. Einstein was at the Institute for Advanced Study, also in Princeton, just a few miles away. He read the book and was impressed. He invited Bohm to come and talk. That conversation between the greatest physicist of the 20th century and a brilliant young professor who was just beginning to question the foundations of his field was one of the most consequential meetings in the history of physics. Einstein told Bohm that he believed quantum mechanics was incomplete, that there must be deeper variables hidden beneath the quantum randomness that determine the outcomes of measurements, that the wave function does not tell the whole story. Bohm listened, he thought, and he went home with a question burning in his mind. What if Einstein is right? What if I can actually construct a theory with hidden variables that reproduces all the predictions of quantum mechanics? What Bohm did next was extraordinary. In a matter of months, he constructed exactly such a theory, and he did not construct it from scratch. He rediscovered and completed an approach that had been proposed 25 years earlier by Louis de Broglie, the French physicist who had first suggested that particles have wave-like properties. De Broglie had proposed a version of pilot wave theory at the 1927 Solvay Conference, one of the most famous gatherings in the history of physics. But de Broglie's proposal was incomplete, and it was aggressively attacked by Wolfgang Pauli, who pointed out what seemed to be a fatal flaw. De Broglie, intimidated by the criticism and by the overwhelming authority of Bohr and Heisenberg, abandoned his own idea. He capitulated. He joined the Copenhagen camp, and pilot wave theory was forgotten for 25 years. Think about that. Let it sink in. De Broglie had the right idea in 1927, 25 years before Bohm's papers. If de Broglie had not been talked out of his own theory, the entire history of quantum mechanics might be different. The measurement problem might have been solved a quarter of a century earlier. Generations of physicists might have been taught a completely different understanding of quantum reality. But one intimidating exchange at one conference changed everything. The power of social pressure in science, the power of authority, of reputation, of peer pressure, is not to be underestimated. It can suppress truth for decades. In January 1952, Bohm published 2 papers in the Physical Review, one of the most prestigious physics journals in the world. The papers were titled, "A Suggested Interpretation of the Quantum Theory in Terms of Hidden Variables 1," and "A Suggested Interpretation of the Quantum Theory in Terms of Hidden Variables 2." And what these papers contained was nothing less than a complete solution to the measurement problem. Let me explain what Bohm proposed, carefully and in detail, because this is the heart of the story. Bohm's theory, which is now known as Bohmian mechanics or pilot wave theory, rests on a beautifully simple idea. In standard quantum mechanics, we have the wave function, and we have the particle, and the relationship between them is mysterious and undefined. The wave function evolves smoothly according to the Schrödinger equation, and then suddenly and inexplicably collapses when a measurement occurs. Bohm's insight was to take both the wave function and the particle seriously, to treat them both as real physical entities, and to specify a precise mathematical relationship between them. In Bohm's theory, a particle always has a definite position. Always. At every moment in time, regardless of whether anyone is looking. This is the hidden variable, the particle's actual position, which quantum mechanics does not describe. The wave function is also real. It is a physical field, like an electromagnetic field or a gravitational field, that fills space and guides the particle. Bohm called it the pilot wave, and the name is perfect because the wave function literally pilots the particle. It tells the particle where to go, like a GPS guiding a car. The particle follows the wave function's instructions, moving along a definite trajectory through space at every moment. The theory has 2 equations. The first is the Schrödinger equation, completely unchanged. The wave function evolves in time exactly as standard quantum mechanics says it does. Bohm did not modify the Schrödinger equation at all. The second equation is new. It is called the guidance equation, and it specifies how the particle's velocity at any moment depends on the wave function at the particle's position. The guidance equation is simple, elegant, and deterministic. Given the wave function and the particle's initial position, the guidance equation tells you exactly how the particle will move for all time. There is no randomness, there is no collapse. There is only the wave function, guiding the particle along a definite path. Now, let me show you how this solves the double-slit experiment, because this is where the beauty of Bohm's theory becomes vivid and tangible. In the double-slit experiment, according to Bohm, the electron is always a particle. It always has a definite position. It goes through one slit or the other, never both. But the pilot wave, the wave function, goes through both slits. The wave function is a field, and fields can spread out, pass through both slits, and interfere with themselves on the other side. The interference pattern in the pilot wave creates a complex landscape of peaks and valleys, channels and barriers, and the particle, guided by the pilot wave, follows this landscape. It is steered by the wave function into the regions where the wave function has large amplitude and away from the regions where it has small amplitude. The result is that even though each individual particle goes through only one slit, the collection of particles, each guided by the same interfering pilot wave, builds up the interference pattern on the screen. When you place a detector at one of the slits, the detector interacts with the pilot wave. It changes the wave function. The interference pattern in the pilot wave is disrupted, and because the particles are guided by the pilot wave, the changed wave function guides the particles differently. The interference pattern disappears, and you get 2 bands, just as you would expect for classical particles. There is no collapse. There is no mystery. There is no observer effect in any deep sense. The detector is a physical device that physically interacts with the pilot wave. That is all. The mystery of the double-slit experiment, which has baffled students and physicists for a century, has a simple, clear, physical explanation in Bohm's theory. Let me now show you how Bohm's theory solves Schrödinger's cat. In the standard interpretation, the cat is in a superposition of alive and dead until someone opens the box. In Bohm's theory, the cat is always either alive or dead. Always, at every moment. The wave function of the system does describe a superposition, yes. The wave function has a branch where the atom decayed and the cat is dead, and a branch where the atom did not decay and the cat is alive. Both branches exist as part of the wave function. But the particle, the actual physical state of the atom, the Geiger counter, the poison vial, the cat, is always in one definite branch. The cat is always either alive or dead, never both. The other branch of the wave function still exists mathematically, but it has no particles in it. It is an empty wave, propagating through a region of configuration space that is no longer occupied. It becomes, for all practical purposes, irrelevant. There is no collapse. The wave function never collapses. It continues to evolve according to the Schrödinger equation forever. But the particle is always in one definite state, and that is the state that corresponds to the actual physical reality. This is so elegant, so natural, so obviously sensible that when you first understand it, you want to shout. You want to grab every physicist in the world by the shoulders and say, "Why did nobody tell me about this? Why was I taught that quantum mechanics is mysterious and paradoxical and beyond human understanding, when there has been a perfectly clear, perfectly comprehensible explanation sitting right there since 1952? Let me address the measurement problem directly. In Bohm's theory, there is no measurement problem. There is no special process called measurement. Measurement is just a physical interaction between the system being measured and the measuring device. Both are made of particles, both are guided by the pilot wave, and both evolved deterministically according to the Schrödinger equation and the guidance equation. When you measure the position of an electron, what happens physically is that the electron interacts with the detector, the pilot wave changes in response, and the particle ends up in a definite state that correlates with the reading on the detector. There is no collapse, no undefined terms, no arbitrary boundary between quantum and classical. The theory is seamless from the smallest subatomic particle to the largest measuring device. Everything is quantum. Everything is guided by the wave function, and everything is definite at all times. But what about the randomness? Quantum mechanics is famous for its randomness. When you measure the position of an electron, you cannot predict exactly where it will be found. You can only predict probabilities. If Bohm's theory is deterministic, where does this randomness come from? The answer is beautiful in its simplicity. In Bohm's theory, the randomness is not fundamental. It is due to ignorance. Each electron has a definite position at all times, but we do not know what that position is. We cannot know, because to determine the exact initial position would require a measurement of infinite precision, which is physically impossible. So, we are forced to describe our ignorance with probabilities. And Bohm showed that if you start with a distribution of initial positions that matches the Born rule, that is, if the probability of finding a particle at a given position is proportional to the square of the wave function at that position, then this distribution is maintained over time. It is, in Bohm's language, the equilibrium distribution. And once in equilibrium, the statistical predictions of Bohm's theory are exactly identical to the statistical predictions of standard quantum mechanics. Every experiment, every test, every observation gives the same result. Bohm's theory and standard quantum mechanics are empirically equivalent. You cannot tell them apart by any experiment. Let me say that again, because it is crucial. Bohm's theory makes exactly the same predictions as standard quantum mechanics for every experiment that has ever been performed or could ever be performed, given current technology. It is not an approximation. It is not close. It is exact. Every prediction, every number, every probability identical. The two theories are empirically indistinguishable. The only difference is in what they say about reality. Standard quantum mechanics says reality is fuzzy, undefined, created by measurement. Bohm's theory says reality is definite, precise, existing at all times, and merely revealed by measurement. The mathematics is the same. The physics is the same. The metaphysics is completely different. And this is why Bohm's theory is so threatening to the Copenhagen establishment. If the two theories make the same predictions, then the choice between them is a choice about what you believe reality is. And if Bohm's theory is a viable option, then the Copenhagen claim that quantum mechanics is complete, that there are no hidden variables, that reality does not exist until observed. All of this is a choice, not a necessity. It is a philosophical preference, not a scientific conclusion. And the Copenhagen physicists had been selling their philosophical preference as scientific fact for 25 years. Bohm's papers pulled the rug out from under them. David Bohm solved the measurement problem. In January 1952, in 2 papers published in the Physical Review, he showed that particles can have definite positions at all times. He showed that the wave function is a real physical field that guides particles along definite trajectories. He showed that measurement is just a physical interaction, not a magical collapse of reality. He showed that the randomness of quantum mechanics is due to ignorance, not fundamental indeterminacy. He showed that reality is real. You would think this would be the biggest news in physics. You would think Bohm would be celebrated, lauded, nominated for the Nobel Prize. You would think textbooks would be rewritten, courses redesigned, the Copenhagen Interpretation relegated to a historical footnote. You would think the measurement problem, having been solved, would be crossed off the list. That is not what happened. What happened instead is one of the darkest, most disturbing, most revealing chapters in the history of science. What happened is that the physics establishment turned on David Bohm with a ferocity that is breathtaking even now, 70 years later. They did not refute his theory. They could not. The mathematics was correct. The predictions were identical. Instead, they dismissed it, ridiculed it, and ignored it, and the man himself was destroyed. To understand the suppression of Bohm's theory, you need to understand the historical context. You need to understand what was happening in America in the early 1950s, because the story of Bohm's theory cannot be separated from the story of McCarthyism, the Cold War, and the Red Scare. In the late 1940s and early 1950s, the United States was gripped by a paranoid fear of communism. Senator Joseph McCarthy and the House Un-American Activities Committee, known as HUAC, were conducting witch hunts, accusing citizens of communist sympathies and destroying careers, reputations, and lives. The scientific community was not immune, far from it. Many scientists, particularly those who had worked on the Manhattan Project, had leftist political sympathies. Some had been members of the Communist Party in the 1930s and 1940s, when it was a legal political party and attracted many idealistic young people who were drawn to its promises of social justice. David Bohm was one of them. As a young man at Berkeley, he had attended meetings of the Communist Party. He was not a committed ideologue. By most accounts, he was a humanist and a pacifist who was attracted to the Communist Party's anti-fascist stance during the fight against Nazi Germany. But in the paranoid atmosphere of McCarthyism, any association with the Communist Party, however brief or marginal, was enough to destroy a person. In 1949, Bohm was called before HUAC. He was asked to testify about his colleagues, to name names, to inform on fellow scientists who might have communist sympathies. Bohm refused. He invoked the Fifth Amendment and declined to testify. This was his legal right, but the consequences were devastating. Bohm was arrested, charged with contempt of Congress, and put on trial. He was eventually acquitted. The courts upheld his right to invoke the Fifth Amendment. But Princeton University, despite the acquittal, suspended him. He was not allowed to set foot on campus. He was not allowed to teach. His contract was not renewed. Einstein, who was by then the most famous scientist in the world, tried to intervene. He lobbied to get Bohm a position at the Institute for Advanced Study, to the intellectual haven in Princeton where Einstein himself worked. But the Institute's director, Robert Oppenheimer, Bohm's own former doctoral advisor, refused. Oppenheimer, himself under investigation for his own leftist associations, was desperate to appear loyal and patriotic. He could not afford to be seen supporting a suspected communist. So he turned his back on his own student. Bohm was left with no position, no prospects, and no future in American physics. In 1951, he left the United States for Brazil, taking a position at the University of São Paulo. His American passport was confiscated by the U.S. Embassy. He was told he could not return to the United States. The man who was about to solve the deepest problem in physics was, in effect, exiled from his own country. It was in this context, as a political exile in Brazil, stripped of his passport, cut off from the major physics centers of the world, that Bohm published his two 1952 papers, and the reaction of the physics establishment was immediate, hostile, and coordinated. Niels Bohr dismissed Bohm's theory without serious engagement. He called it superfluous, unnecessary, because the Copenhagen Interpretation already provided a complete description of quantum phenomena. But this was circular reasoning. Bohr was saying that hidden variables were unnecessary because the Copenhagen Interpretation said they were unnecessary. He was not engaging with Bohm's actual arguments. He was not explaining why Bohm's theory was wrong. He was simply asserting that it was not needed, based on the very assumptions that Bohm's theory challenged. Werner Heisenberg was more aggressive. He attacked Bohm in print, calling his theory ideological, a word chosen with deliberate malice. In the context of the Cold War and McCarthyism, calling a theory ideological was a coded way of calling it communist. Heisenberg was not just criticizing the physics. He was painting Bohm as politically suspect, leveraging the Red Scare to discredit a scientific theory. This was not science. This was character assassination disguised as scientific criticism. Wolfgang Pauli, one of the most brilliant and feared physicists of the 20th century, known for his devastating wit and his willingness to demolish bad ideas in public, initially engaged with Bohm's theory. He exchanged letters with Bohm, raising objections. But when Bohm answered the objections, Pauli turned hostile. He dismissed the theory as artificial and metaphysical, which, from Pauli, it was the ultimate insult. Pauli did not demonstrate that Bohm's theory was mathematically wrong. He did not show that it made incorrect predictions. He simply declared it distasteful. But the most damning response came from J. Robert Oppenheimer, the man who had been Bohm's doctoral advisor, the man who had trained him, the man who had seen his brilliance firsthand. Oppenheimer said, and I want you to read these words carefully because they are among the most revealing words ever spoken by a scientist. If we cannot disprove Bohm, then we must agree to ignore him. Let those words sink in. If we cannot disprove Bohm, then we must agree to ignore him. Oppenheimer did not say Bohm was wrong. He did not say the theory had errors. He did not say the mathematics was flawed. He said that if they cannot disprove it, they must ignore it. This is not science. This is not the pursuit of truth. This is the suppression of truth. This is a powerful figure in physics explicitly calling for the silencing of a valid scientific theory, not because it is wrong, but because it is threatening. And Leon Rosenfeld, who was Niels Bohr's closest ally and most aggressive defender, went even further. Rosenfeld called Bohm's theory a public nuisance. He actively lobbied against it, writing letters to physicists warning them not to take it seriously, pressuring journals not to publish work on hidden variables, and using his considerable influence to ensure that Bohm's ideas remained on the margins of physics. Rosenfeld's behavior was, by any reasonable standard, a violation of scientific ethics. He was not arguing against Bohm's theory on scientific grounds. He was conducting a political campaign to suppress it. Now, you might wonder, how could these brilliant physicists dismiss a valid theory so easily? How could they ignore a solution to the deepest problem in their field? Part of the answer lies in the Cold War context. Bohm was a suspected communist, an exile, a pariah. Supporting his work was politically risky, but there was another factor, one that is perhaps even more important, the von Neumann impossibility proof. In 1932, John von Neumann, the Hungarian-American mathematician who was one of the most towering intellects of the 20th century, published a book called Mathematical Foundations of Quantum Mechanics. In this book, von Neumann included a mathematical proof that hidden variable theories were impossible. He proved, or claimed to prove, that no theory with hidden variables could reproduce the predictions of quantum mechanics. This proof was widely accepted. It was cited in textbooks. It was taught in courses. For decades, any physicist who questioned the completeness of quantum mechanics was told, von Neumann proved that hidden variables are impossible. End of discussion. But here's the thing. The proof was wrong. Von Neumann's proof contained a subtle but critical error. He made an assumption, a mathematical assumption about how hidden variables must behave, that is not physically justified. The assumption seemed reasonable at first glance, but it was too restrictive. It excluded the very type of hidden variable theory that Bohm would later construct. Von Neumann essentially proved that a certain very specific type of hidden variable theory is impossible, and then the physics community generalized this to mean that all hidden variable theories are impossible. It was like proving that you cannot fit a square peg in a round hole, and then concluding that you cannot fit any peg in any hole. And here is the most scandalous part. The error in von Neumann's proof was not discovered by some obscure mathematician decades later. It was pointed out in 1935, 17 years before Bohm's papers, by a German mathematician named Grete Hermann. Hermann published a clear, correct analysis showing that von Neumann's assumption was unjustified and that his proof did not rule out all hidden variable theories. But Hermann was a woman working in philosophy of physics in the 1930s, a time when women were not taken seriously in either field. Her paper was published in a relatively obscure journal. It was ignored, completely ignored, for decades. So let us take stock of the situation. In 1935, Grete Hermann showed that von Neumann's impossibility proof was flawed. In 1952, David Bohm constructed a hidden variable theory that was a living, breathing counterexample to von Neumann's proof. It existed, it worked, and it reproduced all quantum predictions. And yet, for years after 1952, physicists continued to cite von Neumann's proof as the reason hidden variables were impossible. They used a known-to-be-wrong proof to dismiss a known-to-be-correct theory. This is not a conspiracy theory. This is documented history. The papers exist. The citations exist. The letters exist. And it raises a profoundly uncomfortable question. How much of what passes for scientific consensus is actually based on science? And how much is based on social pressure, institutional power, and intellectual laziness? The suppression of Bohm's theory was not a top-down conspiracy in the traditional sense. There was no secret meeting where physicists agreed to bury it. It was more subtle than that, and in some ways more insidious. It was a social phenomenon, a cultural phenomenon, operating through the ordinary mechanisms of academic life. Graduate students were advised by their mentors not to work on foundations of quantum mechanics. It was career suicide, they were told. You will not get a job. You will not get funding. You will not get published. This advice was not wrong. It was accurate, given the culture of the time. But the culture of the time was itself the problem. Funding agencies would not fund research on hidden variables or the measurement problem. Grant applications that mentioned these topics were quietly declined. The message was clear. These are not legitimate research questions. Journals, too, were reluctant to publish papers on quantum foundations. Referees would recommend rejection, not on the basis of mathematical errors, but on the basis of taste. The work was unphysical, metaphysical, not useful. These are not scientific objections. They are cultural objections. They are expressions of orthodoxy, not evidence. And senior physicists, the gatekeepers of the field, openly mocked anyone who questioned Copenhagen. If you raised the measurement problem at a conference, you were likely to be met with a condescending smile and a pat on the head. We settled this in the 1920s, they would say. Bohr already answered these questions. You clearly do not understand quantum mechanics. This was the shut up and calculate culture at its most toxic. It was not just that certain questions were discouraged. It was that the very act of questioning was treated as a sign of ignorance, of philosophical confusion, of not being a serious physicist. The result was a kind of intellectual monoculture. An entire generation of physicists was trained to accept the Copenhagen Interpretation as the final word, to see the measurement problem as either solved or unsolvable, and to view hidden variables as impossible, disproven, absurd. Alternative interpretations were not discussed in textbooks. Bohm's name was not mentioned in courses on quantum mechanics. Students who stumbled across his papers on their own were told they were wasting their time. The suppression was so effective that by the 1970s and 1980s, most working physicists had literally never heard of Bohmian mechanics. A complete, mathematically rigorous, empirically adequate solution to the deepest problem in physics had been erased from the collective memory of the physics community. And through all of this, David Bohm endured. In Brazil, isolated from the centers of physics, cut off from his colleagues, his passport confiscated, his career in ruins, he kept working. He continued to think about the foundations of quantum mechanics. He continued to develop his ideas. He made important contributions to plasma physics, discovering a phenomenon now known as Bohm diffusion. He was not idle, he was not broken, but he was alone, and the loneliness took its toll. By many accounts, Bohm suffered from periods of depression during his years in Brazil. He was a man who had solved one of the greatest problems in science and been punished for it. He was a man without a country, without recognition, without a community of peers who understood or valued his work. Eventually, Bohm moved to Israel, taking a position at the Technion in Haifa. Then, in 1957, he moved to England, where he took a position at Birkbeck College, part of the University of London. He would spend the rest of his career there, working on the margins of mainstream physics but never abandoning his ideas. He continued to refine pilot wave theory. He developed deeper philosophical ideas about what he called the implicate order, a vision of reality as a fundamental wholeness from which the separate objects and events of our experience are merely projections. He engaged with neuroscience, with consciousness research, with Eastern philosophy. He had a remarkable series of dialogues with the Indian philosopher Jiddu Krishnamurti, exploring the nature of thought, perception, and reality. He became, in a sense, more than a physicist. He became a thinker of extraordinary breadth and depth, wrestling with the biggest questions about the nature of existence. But the mainstream physics community continued to ignore him. His work on hidden variables was not cited. His ideas were not discussed at major conferences. His name was absent from the major textbooks. And the measurement problem, the problem he had solved, continued to be described as unsolved, as mysterious, as the deep paradox at the heart of quantum mechanics. It was as if Bohm's solution did not exist, as if it had never been published. David Bohm died on October 27, 1992, at the age of 74. He had a heart attack in a London taxi. He never received the Nobel Prize. He never received the widespread recognition that his work deserved. He lived and died on the margins of the field he had helped to transform. And the measurement problem, the problem he solved in 1952, is still, in most textbooks, described as unsolved. I want to pause here for a moment. I want to give you a moment to sit with this. Because what happened to David Bohm is not just a story about physics. It is a story about human nature. It is a story about how institutions, even institutions dedicated to truth, can become instruments of suppression when they are challenged. It is a story about how the greatest enemy of truth is not ignorance, but the illusion of knowledge. It is a story about how the courage to think differently is the most valuable and the most punished quality in science. But this story does not end with Bohm's exile. It does not end with the suppression. Because the truth has a stubborn quality. It refuses to stay buried. And the man who would dig it up, who would vindicate Bohm and blow the doors off the Copenhagen Consensus, was an Irish physicist working at CERN, the European Nuclear Research Center in Geneva. His name was John Stuart Bell, and his discovery, known as Bell's theorem, is arguably the most profound result in the history of physics. I know we have been going deep for a while now, and I want to check in with you. Are you still with me? Because what comes next is the most intellectually thrilling part of this entire story. We have seen the problem. We have seen the solution. We have seen the suppression. And now we are about to see the vindication. So if you are still here, if you are still engaged, if your mind is still hungry, drop a comment right now. Tell me what you're thinking. Tell me what surprised you the most so far, and hit that like button, because this content takes an enormous amount of research and effort to create, and your support is what makes it possible. John Bell was born in Belfast, Northern Ireland, in 1928. He was the son of a horse trader, and he grew up in a working-class family far from the elite circles of theoretical physics. But Bell was extraordinarily talented, and he worked his way through university, eventually joining CERN as a particle physicist. Bell's day job was accelerator physics, designing and analyzing particle experiments. But his real passion was the foundations of quantum mechanics. He had been troubled by the measurement problem since he was a student, and he had read Bohm's papers with great interest. In fact, Bell later said that reading Bohm's 1952 papers was one of the most significant intellectual experiences of his life. He said, and I quote, "I saw the impossible done." He saw a hidden variable theory that actually worked. that reproduced all the predictions of quantum mechanics that solved the measurement problem. And he was stunned that the physics community had ignored it. Bell was not a flamboyant personality. He was quiet, modest, precise, and deeply honest. He was the antithesis of the big egos and power players that had dominated the quantum foundations debate. He was also fearless. He knew that working on foundations was career poison. He knew that his colleagues at CERN would think he was wasting his time. He did it anyway, because he cared more about truth than about reputation. Bell set out to understand exactly what constraints nature places on hidden variable theories. He knew that Bohm's theory worked, which meant that von Neumann's impossibility proof must be wrong. He independently confirmed that von Neumann's proof contained an unjustified assumption, exactly as Greta Herrmann had shown decades earlier. But Bell wanted to go further. He wanted to know, are there any constraints on hidden variable theories? Can any hidden variable theory reproduce the predictions of quantum mechanics, or are there limits? The answer he found, published in a paper in 1964, was one of the most profound discoveries in the history of science. Bell's theorem, as it is now known, showed that there is a constraint on hidden variable theories, but it is not the constraint that von Neumann proposed. The constraint is locality. A local hidden variable theory, one in which the hidden variables at one location are not influenced by events at distant locations, cannot reproduce all the predictions of quantum mechanics. The predictions of quantum mechanics violate a mathematical inequality, now known as Bell's inequality, that any local hidden variable theory must satisfy. Let me explain what this means because it is absolutely crucial. Locality is the principle that things are only directly influenced by their immediate surroundings. If I snap my fingers here, it does not instantly affect a particle on the other side of the galaxy. Any influence must travel through space, and nothing can travel faster than light. This is one of the foundational principles of Einstein's theory of relativity, and Bell showed that if you insist on locality, if you insist that hidden variables at one location cannot be instantaneously influenced by measurements at a distant location, then the predictions of any such theory will satisfy a certain mathematical inequality, and quantum mechanics violates that inequality. The quantum predictions are more strongly correlated than any local hidden variable theory can produce. This is a stunning result. It means that if quantum mechanics is correct, and every experiment ever performed confirms that it is, then nature is non-local. There are correlations between distant events that cannot be explained by any local mechanism. Einstein's spooky action at a distance is real. When two entangled particles are separated by vast distances and you measure one, the result is instantaneously correlated with the result you would get if you measured the other, in a way that cannot be explained by any local theory. Now, here is the key point for our story. Bell's theorem does not rule out Bohm's theory. Bohm's theory is non-local. The pilot wave connects all particles in the universe, and a change in the wave function at one location can instantaneously affect the guidance of a particle at a distant location. This non-locality was often cited as a weakness of Bohm's theory. Critics said it was unphysical, that it violated the spirit of relativity. But Bell showed that non-locality is not a weakness of Bohm's theory. It is a feature. It is a requirement. Any theory that reproduces the predictions of quantum mechanics must be non-local. Bohm's theory is non-local because nature is non-local. The non-locality is not a bug in Bohm's theory. It is a deep truth about reality that Bohm's theory makes explicit. Bell's theorem also showed something else. It showed that the choice between interpretations of quantum mechanics is not just a matter of taste or philosophy. It has empirical consequences. Bell derived a specific inequality that can be tested in the laboratory. If the inequality is violated, then nature is non-local. If it is not violated, then a local hidden variable theory might work. This was the first time in history that a philosophical question about the nature of reality was turned into a testable, experimental prediction, and physicists immediately set about testing it. The first definitive experiments were performed by Alain Aspect and his team at the University of Paris-Sud in 1982. Aspect used pairs of entangled photons and measured their polarizations at different angles. The results were unambiguous. Bell's inequality was violated. Nature is non-local. The quantum predictions were confirmed. Local hidden variable theories were ruled out, and Bohm's non-local theory remained standing. Over the following decades, increasingly precise experiments were performed, closing one potential loophole after another. John Clauser had performed earlier experiments in the 1970s. Anton Zeilinger and his team performed some of the most impressive experiments in the 2000s and 2010s, closing the so-called locality loophole and the detection loophole in a single experiment. The results were always the same. Bell's inequality is violated. Nature is non-local. Quantum mechanics is correct. And in 2022, the ultimate vindication came. Alain Aspect, John Clauser, and Anton Zeilinger were awarded the Nobel Prize in Physics for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. Their Nobel-winning work was built on Bell's theorem, and Bell's theorem was inspired by Bohm. The intellectual lineage is direct. Bohm's hidden variables led to Bell's theorem, which led to Aspect's experiments, or which led to the Nobel Prize. Bohm was the starting point. Without Bohm, there would be no Bell's theorem. Without Bell's theorem, there would be no experimental tests. Without the experimental tests, there would be no Nobel Prize. And here is the bitter irony. John Bell himself died of a cerebral hemorrhage in 1990 at the age of 62. He was widely expected to receive the Nobel Prize. Many physicists believe he would have shared it with Aspect, Clauser, and Zeilinger if he had lived. He did not live to see his vindication. And David Bohm, who started it all, who solved the measurement problem in 1952, who endured exile and suppression for decades, died in 1992 without ever receiving the Nobel Prize or the widespread recognition he deserved. The two men most responsible for our deepest understanding of quantum reality, the man who showed that hidden variables work and the man who showed what hidden variables require, were never awarded physics' highest honor. The prize went to the experimentalists who confirmed their ideas. The ideas themselves, the revolutionary, paradigm-shifting, reality-redefining ideas, were never honored. I want to dwell on Bell's own views for a moment, because they are extraordinarily relevant to our story. Bell was not coy about his sympathies. He openly admired Bohm's theory and wrote several papers defending it. He argued, persuasively, that Bohm's theory should be taught alongside the Copenhagen Interpretation in every quantum mechanics course. He was scathing about the Copenhagen school. In a famous essay titled Against Measurement, Bell wrote, "The word measurement has now been used so indiscriminately that it is impossible to give it a precise meaning. It has become a parasite on physics, a term that adds nothing and obscures much." He argued that the Copenhagen Interpretation's reliance on the undefined concept of measurement was unprofessionally vague and ambiguous, words I quoted earlier. He said, "The founding fathers of quantum mechanics were wrong about what they had done." This is John Bell, one of the most important physicists of the 20th century, saying that Bohr, Heisenberg, and the Copenhagen school were wrong. Not about the mathematics, which is correct, but about what the mathematics means, about reality itself. Bell's work had a transformative effect on the field. It did not immediately overthrow Copenhagen. Institutional inertia is powerful, and textbooks change slowly, but it made it scientifically respectable to question Copenhagen again. It showed that foundational questions about quantum mechanics were not idle philosophy. They led to testable predictions and profound discoveries. It inspired a new generation of physicists to take the foundations of quantum mechanics seriously. And it set the stage for the renaissance that is happening right now. Let me tell you about that renaissance. Starting in the 1990s and accelerating through the 2000s and into the present, the foundations of quantum mechanics have become one of the most vibrant and exciting areas of physics research. Annual conferences on quantum foundations now attract hundreds of physicists from around the world. Papers on the measurement problem, hidden variables, the interpretation of quantum mechanics, and related topics are regularly published in the most prestigious journals. Shut up and calculate is no longer the dominant attitude. A new generation of physicists, raised on Bell's theorem and inspired by his example, is asking the questions that the Copenhagen school forbade. Bohmian mechanics, in particular, has experienced a stunning revival. The theory has been refined and extended far beyond Bohm's original papers. A trio of physicists, Detlef Durr, Sheldon Goldstein, and Nino Zheng He, have been the primary champions of Bohmian mechanics in the modern era, providing rigorous mathematical foundations, extending the theory to multi-particle systems, developing Bohmian approaches to quantum field theory, and demonstrating that the quantum equilibrium hypothesis, the assumption that initial particle positions are distributed according to the Born rule, can be justified on general grounds, much like the assumption of thermal equilibrium in classical statistical mechanics. Their work has shown that Bohmian mechanics is not just a historical curiosity, but a living, breathing research program with deep insights and important results. Other physicists have contributed to the Bohmian program from different angles. Some have worked on developing Bohmian quantum field theory, which is more technically challenging than non-relativistic Bohmian mechanics, but has made significant progress. Others have explored the implications of Bohmian mechanics for quantum cosmology, the application of quantum mechanics to the entire universe. In standard quantum mechanics, quantum cosmology is plagued by the measurement problem, because there is no external observer to measure the universe. Who collapses the wave function of the universe? In Bohmian mechanics, this is not a problem. The universe has a definite configuration at all times, guided by a universal wave function. There is no need for an external observer, no collapse, no mystery. Now, I should be honest and tell you that Bohmian mechanics is not the only alternative to the Copenhagen interpretation. There are several other interpretations that have been developed over the decades, each with its own strengths and weaknesses. The many worlds interpretation, proposed by Hugh Everett in 1957, takes a radically different approach. It says that the wave function never collapses. All branches of the superposition are equally real. When a measurement is made, the universe splits into multiple branches, one for each possible outcome. You and the cat both exist in all branches, but each version of you only experiences one outcome. The measurement problem is solved by saying that every outcome happens in different branches of reality. This is a bold and mathematically elegant approach, but it has its own problems. It is not clear how to derive the Born rule probabilities from the many worlds framework. It is not clear what it means for a universe to split, and it requires an extravagant ontology. Infinitely many copies of every object in the universe, branching at every quantum event. The GRW theory, proposed by Ghirardi, Rimini, and Weber in 1986, takes yet another approach. it modifies the Schrödinger equation by adding a tiny, spontaneous collapse mechanism. Every particle has a very small probability of undergoing a spontaneous localization, a sudden narrowing of its wave function to a small region of space. For a single particle, these collapses are so rare that they are undetectable. But for a macroscopic object containing trillions of particles, the collapses happen very frequently, keeping the object in a definite state at all times. This approach solves the measurement problem by making collapse a real physical process with a definite mechanism, rather than an undefined postulate. But it requires modifying the Schrödinger equation, which means it is, in principle, experimentally distinguishable from standard quantum mechanics. So far, no experiment has detected the GRW modifications, and the parameters of the theory are constrained, but not yet ruled out. Cubism, or quantum Bayesianism, is a more recent approach that takes the Copenhagen idea of the wave function as knowledge and pushes it much further. In cubism, the wave function represents an individual agent's beliefs about the outcomes of future measurements. Different agents can have different wave functions for the same system. Measurement outcomes are personal experiences of the agent. This approach dissolves the measurement problem by making quantum mechanics a theory about agents' beliefs rather than a theory about the physical world. But many physicists find this unsatisfying. It seems to give up on the idea that physics describes an objective reality. Relational quantum mechanics, proposed by Carlo Rovelli, takes a similar but distinct approach, suggesting that the properties of quantum systems are not absolute, but relative to other systems. A particle does not have a definite position in itself. It has a definite position relative to a particular observer. Different observers can have different, equally valid descriptions of the same system. This is an intriguing approach with the deep connections to Rovelli's work on quantum gravity, but it raises difficult questions about the consistency of different observers' descriptions. Each of these interpretations has its supporters and its critics. None has achieved the kind of consensus that the Copenhagen Interpretation once enjoyed. And this, in a way, is healthy. It reflects the genuine difficulty of the measurement problem and the diversity of approaches to solving it. But when you compare these interpretations side by side, Bohmian mechanics has a unique advantage. It is the only interpretation that provides a clear, unambiguous, detailed physical picture of what is happening at all times, while reproducing all the predictions of standard quantum mechanics exactly. Many worlds requires an infinite ontology. GRW requires modifying the fundamental equations. Cubism and relational quantum mechanics give up on objective reality. Bohmian mechanics gives you everything: definite particles, a real wave function, deterministic dynamics, no collapse, no mystery, and all the correct predictions. The price you pay is non-locality, but as Bell showed, non-locality is the price any correct theory must pay. I should mention one more remarkable development that has brought pilot wave theory vividly to life. In the 2000s, a group of physicists in France, led by Yves Coudet and Emmanuel Fort, discovered something astonishing. They found that tiny silicone oil droplets bouncing on the surface of a vibrating fluid bath create their own waves, and these waves guide the droplets, just as the pilot wave guides particles in Bohm's theory. The droplets are macroscopic. You can see them with the naked eye, and they exhibit behaviors that are eerily similar to quantum phenomena. When these bouncing droplets are sent toward a barrier with two slits, the collection of droplets builds up an interference pattern on the other side. Single droplets, passing through the barrier one at a time, somehow collectively produce a pattern that mirrors the quantum double-slit experiment. The reason is exactly what Bohm proposed. The droplet goes through one slit, but the wave it creates goes through both, and the interference pattern in the wave guides the droplet's trajectory. When the droplets are confined in a circular corral, they settle into quantized orbits, discrete, stable paths that mirror the quantized energy levels of atomic electrons. When the droplets encounter a barrier that they should not be able to cross, they sometimes tunnel through, just like quantum particles tunnel through potential barriers. Now, I must be clear about something important. These bouncing oil droplets are a classical analog of quantum pilot waves. They are not actual quantum pilot waves. The analogy is not perfect, and there are important differences between the classical bouncing droplets and the quantum pilot wave. But what these experiments show is that the pilot wave concept is not abstract or mystical. It is physically intuitive. You can see it. You can watch a droplet being guided by its wave. You can see the interference pattern building up. You can see the quantized orbits forming. For the first time, pilot wave theory is not just a set of equations on a page. It is a physical reality that you can observe with your own eyes. And when you watch these experiments, and I encourage you to look them up after this video, you cannot help but think, maybe this is what is really happening at the quantum level. Maybe Bohm was right all along. Now, I want to take you to the deepest level. I want to explore the implications of Bohm's theory for our understanding of reality itself. Because if Bohm is right, if pilot wave theory is the correct description of quantum mechanics, then the consequences are profound, far-reaching, and, in many ways, more mind-blowing than anything the Copenhagen Interpretation ever proposed. Let us start with determinism. If Bohm is right, the universe is deterministic. Every particle has a definite position at every moment in time, and that position evolves according to deterministic equations. The future is completely determined by the present. The randomness we observe in quantum experiments is not fundamental. It is a consequence of our ignorance of the precise initial conditions. Just as the outcome of a coin flip is determined by the exact angle, force, and air resistance of the throw, even though we perceive it as random, the outcome of a quantum measurement is determined by the exact initial position of the particle, even though we perceive it as random. In Bohm's universe, God does not play dice. Einstein was right. But what does this mean for free will? If the universe is deterministic, if every particle follows a predetermined path, then every atom in your brain is following a predetermined path, and every thought you think, every choice you make, every action you take is the inevitable consequence of the initial conditions of the universe. Free will, in this picture, would be an illusion, a subjective experience that has no basis in the underlying physics. This is deeply unsettling for many people, and it has been one of the most debated implications of deterministic physics for centuries, going back long before quantum mechanics. But here is an important nuance. In Bohm's theory, even though the dynamics are deterministic, the initial conditions are unknowable. The quantum equilibrium hypothesis states that the distribution of particle positions is given by the Born rule, the square of the wave function, and that this distribution is self-maintaining. Once the universe is in quantum equilibrium, it stays in quantum equilibrium. And quantum equilibrium means that we can never determine the precise positions of all particles. We can never have enough information to predict the future with certainty, even though the future is certain. The universe is a deterministic clock, but it is a clock whose current settings can never be read. This is a subtle and interesting situation. The universe is determined, but it is effectively unpredictable. You are free not because the universe is random, but because you can never know enough to see the determinism. Whether this counts as genuine free will or merely an illusion of it is a philosophical question that I will leave for you to ponder. Now, let us consider non-locality. This is perhaps the most mind-blowing implication of Bohm's theory. In Bohm's theory, the pilot wave connects all particles in the universe. The wave function of the universe is a single, vast, interconnected field, and every particle is guided by this universal wave function. A change in the wave function at one location can instantaneously affect the guidance of a particle at a distant location. There is no limit to the distance over which this connection operates. Two entangled particles on opposite sides of the galaxy are just as connected as two entangled particles in the same laboratory. This means that the universe, in Bohm's picture, is not a collection of separate, independent things. It is a single, interconnected whole. Every particle is connected to every other particle through the pilot wave. Separation, in a deep sense, is an illusion. The separate objects we perceive, you, me, this table, that star, are not truly separate. They are all expressions of a single, unified wave function, like waves on the surface of one ocean. They appear separate when viewed from the surface, but beneath the surface they are all part of the same water. Bohm himself developed this idea extensively in his later work, using the concept of the implicate order. He proposed that the reality we perceive, the world of separate objects and events in space and time, is what he called the explicate order. It is the unfolded, visible, manifest level of reality. But beneath it lies the implicate order, a deeper level of reality where everything is enfolded together, where separateness does not exist, where the entire universe is a single, undivided whole. The explicate order unfolds from the implicate order, like a flower unfolding from a bud. And the implicate order enfolds the explicate order back into itself, like the ocean absorbing a wave. This is a profound vision of reality. It is not just physics, it is a worldview, and it resonates deeply with ideas from various philosophical and spiritual traditions. The interconnectedness of all things is a central theme in many Eastern philosophies, in Buddhism, in Hinduism, and Taoism. The idea that separateness is an illusion, that all things are ultimately one, is expressed in the Upanishads, in Zen Buddhism and Sufi mysticism. But Bohm arrived at this vision not through meditation or revelation. He arrived at it through physics, through mathematics, through the rigorous analysis of quantum mechanics. This is perhaps the most remarkable thing about Bohm's work. It shows that the deepest insights of physics and the deepest insights of philosophical and spiritual traditions are converging on the same picture of reality. I should add a word of caution here. Bohm's ideas about the implicate order are philosophical extensions of his physical theory, not direct consequences of the mathematics. The mathematical formalism of Bohmian mechanics, the Schrödinger equation and the guidance equation, does not by itself tell you about the implicate order or the interconnectedness of all things. These are Bohm's interpretations and extrapolations, and they go beyond the strict domain of physics, but they are informed by physics, motivated by physics, and consistent with physics, and they show the extraordinary depth and breadth of Bohm's thinking. A physicist who was not content to merely solve equations, but who sought to understand the nature of reality itself. Let me also discuss the implications of Bohm's theory for the nature of space and time. In Bohm's theory, non-locality means that distant events can be instantaneously correlated. This seems to conflict with special relativity, which says that nothing can travel faster than light. And indeed, the relationship between Bohmian mechanics and special relativity is one of the major open questions in the field. The non-locality of Bohm's theory is not the kind that allows faster-than-light signaling. You cannot use quantum entanglement to send messages faster than light, because the non-local correlations are hidden behind the randomness of quantum equilibrium. But the non-locality is real, and it suggests that space as we know it may not be fundamental. This idea, that space is not fundamental but emergent from something deeper, is gaining increasing support from other areas of physics, particularly from research on quantum gravity. The holographic principle, which arose from the study of black holes and string theory, suggests that the three-dimensional space we inhabit may be a projection of information encoded on a two-dimensional surface. The ER equals EPR conjecture, proposed by Juan Maldacena and Leonard Susskind, suggests that quantum entanglement and wormholes, tunnels through space-time, are the same thing, that the non-local connections between entangled particles are literally wormholes in the fabric of space-time. If this is correct, then the non-locality of Bohm's theory is not a violation of space-time, but a reflection of its deeper structure. Bohm was, in a very real sense, ahead of his time. Ideas that he proposed in the 1950s are now at the cutting edge of quantum gravity research in the 2020s. There is another implication of Bohm's theory that I find particularly compelling, and it concerns the role of the observer in physics. In the Copenhagen Interpretation, the observer plays a central, almost magical role. The observer causes wave function collapse. The observer creates reality. Without the observer, reality does not exist in a definite form. This has led to all sorts of mystical and pseudoscientific appropriations of quantum mechanics. The idea that you can create your own reality through the power of thought, that consciousness is the fundamental fabric of the universe, that quantum mechanics proves the existence of God or the soul. These ideas are not supported by the physics, and most physicists rightly dismiss them. But in Bohm's theory, the observer has no special role at all. The observer is just another physical system, made of particles guided by the pilot wave, interacting with other physical systems according to the same deterministic equations. There is no collapse, no creation of reality through observation, no special status for consciousness. Reality is real, definite, and independent of observation. The observer is part of reality, not the author of it. This is, in my view, a much more scientifically healthy position. It removes the mystical overtones that have plagued quantum mechanics for a century and puts the theory on a solid, realistic foundation. It means that physics describes an objective reality, not a subjective experience. It means that the universe exists whether anyone is looking at it or not. It means that the moon is there when nobody looks. And yet, even as Bohm's theory removes the mystical role of the observer, it introduces something arguably more profound: the interconnectedness of all things through the pilot wave. The universe, in Bohm's picture, is not a collection of isolated atoms bouncing around in empty space. It is a deeply interconnected whole, in which every particle is related to every other particle through the universal wave function. This is not mysticism, this is physics. It is non-locality made precise and mathematical. And it is, in its own way, far more awe-inspiring than any mystical claim about consciousness creating reality. I want to share with you some stories that do not usually make it into the textbooks. Stories about the people behind the physics, the human drama that unfolded alongside the scientific drama. Because this is, above all, a human story. A story about brilliant, flawed, courageous, and sometimes cowardly human beings, grappling with questions that are bigger than any individual. Consider the story of Louis de Broglie. De Broglie was a French aristocrat, a prince, illiterally, who proposed in his 1924 doctoral thesis that particles have wave-like properties. This idea, for which he won the Nobel Prize in 1929, was one of the cornerstones of quantum mechanics. And de Broglie did not stop there. He developed a pilot wave theory, very similar to what Bohm would later propose, and presented it at the 1927 Solvay Conference. At that conference, the most brilliant physicists in the world gathered to discuss the new quantum theory. de Broglie presented his pilot wave idea, and it was attacked. Wolfgang Pauli raised an objection involving inelastic scattering, arguing that de Broglie's pilot wave could not handle certain types of interactions. De Broglie struggled to respond. He was a quiet, aristocratic man, not a fighter, and he was facing Pauli, one of the most aggressive and intimidating debaters in physics, backed by the authority of Bohr and Heisenberg. De Broglie was overwhelmed. He abandoned his own theory. He joined the Copenhagen camp and spent the next 25 years teaching the interpretation that had defeated him. But here is the thing. Pauli's objection was not fatal. When Bohm revived the pilot wave theory in 1952, he showed how to handle exactly the kind of interaction that Pauli had raised. The objection was answerable. De Broglie had been talked out of a correct theory by an answerable objection, because the social pressure was too great. When Bohm published his papers, de Broglie initially supported them. He even returned to his own pilot wave ideas for a while. But the pressure was relentless, and de Broglie eventually retreated again. He spent the last decades of his life in a kind of intellectual limbo, recognized for his early contributions, but marginalized for his foundational views. He died in 1987, having never seen the vindication that Bell's work would bring.